Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 2, we will discuss about the Rankine cycle. So the Rankine cycle actually is the specific thermodynamic cycle for steam power plant. So in order to analyze any steam power plant, we need to use the Rankine cycle. So in order to discuss about the Rankine cycle, still we need to refer to the simplified schematic diagram for the steam power plant that consists of a pump, a boiler, a turbine, and also a condenser. So where at the pump we will have compression process, at the boiler we will have heat addition process, at the turbine we will have expansion process where the turbine will produce W out, and at the condenser we will have heat rejection process. Okay. So the Rankine cycle actually was introduced in order to eliminating impracticalities in Carnot cycle. So we already discussed the impracticalities of the Carnot cycle in part number 1. Okay, and this TS diagram shows the ideal Rankine cycle that represented by red color cycle. Okay, as we can see in the TS diagram. So we have 4 states involved. Start from state number 1 in saturated liquid, state number 2 in compressed liquid, state number 3 in superheated vapor region, and state number 4 in saturated mixture region. So this Rankine cycle TS diagram refer to the ideal Rankine cycle TS diagram. Okay, so if you compare to the cycle for the Carnot cycle, so the yellow cycle, square cycle, represent the Carnot cycle. Okay, so in order to eliminate impracticalities in Carnot cycle, to make some modification, so we need to add a specific process, which is one of the process is by superheating the steam in the boiler. Okay, so at the beginning in the Carnot cycle, state number 3 is at saturated vapor, where we already discussed that this characteristic will limit the efficiency of the steam power plant. So when we superheating the steam in the boiler, so the state number 3 in Carnot cycle will increase to state number 3 in the Rankine cycle as shown in the TS diagram. So now the phase of the water is superheated, and then the second process we add to the cycle is by condensing the steam completely in the condenser. So in Carnot cycle, the after condensing process, the state number 1 will be in saturated mixture region. Okay, but for Rankine cycle, where we condensing the steam completely in the condenser, at least the water will be in saturated liquid at least. Okay, so sometimes the condition of state number 1 will be in compressed liquid. But for ideal case, the phase for state number 1, the phase for state number 1 will be at saturated liquid condition. Okay, by implementing these two approaches, so we will have the Rankine cycle as shown in the TS diagram. So the Rankine cycle will involve 4 states and 4 processes, and the discussion will refer to the ideal cycle of the Rankine cycle. So if you look at the TS diagram, there are 4 processes. Process number 1 we call isentropic compression process, from state number 1 to state number 2. Okay, so for this process, state number 1 will be at saturated liquid condition, and state number 2 will be at compressed liquid condition, and the process is isentropic due to the value of entropy at state number 2 equal to the value of entropy at state number 1. Okay, so during the process we need to give work, so that's why we have W in during the compression process. So during this process, the pressure will increase from P1 to P2, and the temperature also will increase. during the compression process. Okay, the second process we call the constant pressure heat addition process. Start from state number 2 to state number 3 as shown in the TS diagram. So during the process, the pressure maintained where P3 and also P2 is equal. State number 2 and state number 3 is located at the same constant pressure line. Okay, so the pressure is constant. So during the process, we will have heat addition process Q in the boiler. Okay, so the process, describe process inside the boiler, and we need to supply heat so that the water condition at state number 2 in terms of temperature will increase, and also the pressure is constant, and the phase will change from compressed liquid to superheated vapor. Okay, so next, the third process is isentropic expansion. So the process will occur in the turbine, in the steam turbine, from state number 3 to state number 4. And the process is isentropic because the entropy value at state number 3 will be equal to entropy value at state number 4, because the process is the ideal process. So now at the turbine, so we'll have W out, work produced, and during the process the temperature reduce, the pressure also will reduce. Okay, due to the expansion process, so the energy from the superheated vapor already transferred to the rotor of the turbine. So at state number 4, the water condition is in saturated mixture region. Process number 4, the last one, we call the process as constant pressure heat addition. So during the process, the pressure is constant, where P4 equal to P1, and state number 4 and state number 1 is located on the same constant pressure line. So during the process, we have heat rejection process in the condenser, that represented by Q out. And the state for the condition for state number 4 is saturated mixture, and state number 1 is in saturated liquid. So now we have complete cycle for the Rankine cycle. Okay, the cycle will continue. Okay, so that's how we explain about Rankine cycle in terms of schematic diagram and also TS diagram. So we have 4 processes involved. So the important things that we need to understand about the TS diagram, we need to know what I call the phase for each state in the Rankine cycle. We need to know the process, the characteristic for each process, such as the compression, heat addition, expansion, also heat rejection process. Okay, and also we need to identify state number 1 represent which state in the schematic diagram, and so on. Okay, analysis of the ideal Rankine cycle. So when I mention about the analysis, that means we need to identify the equation that need to be used to determine, for example, the value of Q in, Q out, W in, and W out. And then we need to use this parameter in order to determine the thermal efficiency of the Rankine cycle. Okay, so still we need to refer to this simplified schematic diagram for the steam power plant, and also the TS diagram for the Rankine cycle. For the analysis, we assume that all the devices involved in the steam power plant we consider as the steady flow devices, including the pump, boiler, condenser, and turbine. Okay, so then we can use the steady flow energy balance equation as shown in this slide, where Q in minus Q out plus W in minus W out equal to H exit minus H inlet. So H represent the enthalpy value. Okay, so the value of H exit minus H inlet actually come from the formula for E mass in and also E mass out. Due to the steady flow process, the delta E terms will be 0. So that's why we have this equation. After we rearrange the equation, so we'll get the equation in terms of steady flow and the energy equation for the open system, because individual device such as pump, boiler, turbine, and condenser we consider as the open system, because we have inlet and outlet point for each device. Okay, so in order to determine the formula, we need to apply this equation to specific device in the steam power plant or in the schematic diagram. For example, for the isentropic compression, the device that involved is the pump. So for the pump, we have the parameter involved with W in, where we need to supply W in to the pump. So in order to determine the formula of W in, we can what I call apply the energy balance equation to the pump. Okay, so if you can see at the pump, we will not have any Q in, no Q out, no W out, because now we consider the pump only require W in. So the remaining term for energy balance equation is W in equal to H exit minus H inlet. So H exit for the pump is referred to H2, and H inlet for the pump referred to H number 1. So that's why we have the formula for W pump in equal to H2 minus H1. Okay, so because for the ideal Rankine cycle, the condition for state number 1 is saturated liquid, so we can replace, instead of we just use H1, we can use HF at P1. HF at P1 stands for the enthalpy value at saturated liquid condition, which is referred to the state 1 for ideal Rankine cycle. So for W pump in, we have another equation. Normally we refer to the equation in fluid mechanics, where W pump in equal to V specific volume multiplied by pressure difference P2 minus P1. Pressure at the outlet of the pump minus pressure at the inlet of the pump. Okay, so the equation more or less equal to V1 multiplied by P2 minus P1. And because for the ideal Rankine cycle, state number 1 is saturated liquid, we can replace V1 with VF at P1 multiplied by P2 minus P1. VF stands for the specific volume at the saturated liquid condition. So all this value we can determine from the thermodynamic water table. Okay, now the second equation is for the heat addition process in the boiler from state number 2 to state number 3. So we have the parameter that involved during the process, heat addition process, is Q in. Okay, if we implement energy balance equation to the boiler, so at the boiler we don't have any Q out, no W in, no W out. So the remaining term for the energy balance equation is Q in equal to H exit minus H inlet. For this case, H exit is H3, H inlet for the boiler is H number 2. So that's why we have the formula for Q in equal to H3 minus H2. Okay, now for the third process involved with the expansion process from state number 3 to state number 4 in the turbine. So the parameter that involved during the expansion process is only W out or W turbine out. So if we implement the steady flow energy equation to the turbine, so we will have no Q in, no Q out, and no W in. So the remaining terms will be negative W out equal to H exit minus H inlet. H exit here for the turbine is referred to H4, H inlet referred to H3. So we will have negative W out equal to H4 minus H3. So rearrange the equation, so we will get W turbine out will be equal to H3 minus H4. Okay, so that the equation involved with process number 3. Process number 4 involved with constant pressure heat addition, where the process start from state number 4 to state number 1. The pressure is constant, where P4 is to P1, and the process occur in the condenser. So the parameter that involved for the condenser only Q out. So if we implement the energy balance equation to the condenser, so during the process, heat rejection process, we don't have any Q in, so we have Q out, no W in, no W out. So the remaining term for the equation will be negative Q out equal to H exit H4, sorry H1 minus H inlet H4 for the condenser. So rearrange the equation, so you get Q out equal to H4 minus H1. So you can use all these equation, W in, Q out, W out, in order to determine the thermal efficiency for the Rankine cycle by using the general equation for thermal efficiency, where mu TH equal to W net divided by Q in, or 1 minus Q out divided by Q in, where W net equal to Q in minus Q out, also equal to W out minus W in. Okay, so again, I just want to remind you that the the value, the formula for W pump in equal to V P2 minus P1, you can use for the case when the pressure of the water below than 5 megapascal. But if the value greater than 5 megapascal, it is better to use the compressed liquid table for the water in order to determine the value of H2. Okay, but if the data are not available, still you can use the second formula for W in, where W in equal to V multiplied by P2 minus P1. Example 4.1. Consider a steam power plant operating on the simple Rankine cycle. Simple Rankine cycle here means the ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at the pressure of 75 kilopascal. Determine the thermal efficiency of this cycle. So in terms of data given in terms of the condition at the inlet of the turbine, which is referred to the state number 3. So we have P3 and also T3. It's condensed in the condenser at a pressure of 75 kilopascal, and the question also gives you the data in terms of pressure during the condensing process. So now you need to determine the thermal efficiency of this cycle. Okay, the solution for example 4.1. So now you need to draw this schematic diagram of the ideal Rankine cycle, and also you need to draw the TS diagram based on the question. So you need to put in the data given on this schematic diagram and also on the TS diagram in order to understand the data given in the question for the specific condition of the steam power plant. So we have the data given is for state number 3, where P3 equal to 3 megapascal and also 350 degrees Celsius in terms of temperature at the inlet of the turbine. And the condition in terms of pressure at the condenser is 75 kilopascal. So because during the condensing process we know that the pressure is constant, so now we have the data for P4 75 kilopascal and also P1 also equal to 75 kilopascal. Okay, so on the TS diagram we know that the T3 value will be at 350 degrees Celsius as mentioned in the question. Okay, and also the constant pressure line of 75 kilopascal and also constant pressure line for 3 megapascal. So we have in terms of during heat addition process, we also know that the pressure also constant, where P3 equal to P2 equal to 3 megapascal. So now we need to use all the data to determine the thermal efficiency of the steam power plant. Okay, so determine the thermal efficiency of the cycle. So what you have to do, so you need to determine the important parameter for each state, especially the value of enthalpy, because later on, in order to determine the thermal efficiency, you need to know the enthalpy value to determine Q in value, Q out, W in, and so W out. Okay, so in order to determine the thermal efficiency, we can use this formula, the general formula for thermal efficiency, where thermal efficiency equal to W net divided by Q in equal to 1 minus Q out divided by Q in. And we know that W net also equal to Q in minus Q out, or equal to W out minus W in. So the data given, we know that P3 minus P2, P3 equal to P2 equal to 3 megapascal due to constant pressure heat addition process. T3 already given in the question equal to 350 degrees Celsius, and P4 equal to P1 equal to 75 kilopascal, the constant pressure during heat addition process in the condenser. Okay, first determine the state number 1. So now for the steam power plant analysis, you must know that the working fluid for the steam power plant is water. So in order to determine the enthalpy value, so you need to use the thermodynamic table for the water. So there are 3 types of tables for the water. So we have saturated water table, compressed liquid water table, and also the superheated vapor water table. So for steam power plant analysis, you need to identify the phase of the state, then you can know which table that you need to use in order to determine the enthalpy value for specific states. Okay, for example, for state number 1, so we have pressure 1, P1 equal to 75 kilopascal. So we don't have any other data, but we know that for the ideal Rankine cycle, the phase for state number 1 is at saturated liquid, which means you need to refer to the table of saturated water table. I show in the slide. Okay, by referring to the value of pressure P1 equal to 75 kilopascal, so you can determine the value of H1, where H1 equal to HF at 75 kilopascal. HF represent the enthalpy value at saturated liquid. Okay, F stand for saturated liquid, G stand for saturated vapor. Okay, so because the condition is saturated liquid, so we need to refer to HF, which is equal to 384.39 kJ per kg. And also we can determine the value of V1. So V1 equal to Vf at 75 kilopascal equal to 0.001037 meter cubic per kg. Okay, done for state number 1. For state number 2, we know that state number 2 will involve this isentropic compression process, and the phase for state number 2 actually the compressed liquid. However, if we look at the pressure is 3 megapascal, below 5 megapascal. So if you refer to the compressed liquid table, the data for 3 megapascal is not available if you want to use the compressed liquid table. So we need to use another method, where we know that during the process S2 equal to S1 and the phase compressed liquid, but because the data is not available if you use the compressed liquid table, in order to determine the value of H2, we can use this formula, where W pump in equal to V1 multiplied by P2 minus P1 equal to H2 minus H1. So V1 we already determined from the table, H1 also we already determined from the table, P2, P1 already given in the question. So you can rearrange the equation, so you can determine the value of H2. H2 equal to 387.42 kilojoule per kg. Okay, so now for state number 3, you can look at the data given. So we know that P3 equal to 3 megapascal, and we have additional data that already given in the question, where T3 equal to 350 degrees Celsius. So for the water table, at least you need to have 2 information. So for this case, we already have 2 information, and we can determine the phase, and then we can use the specific table of the water. Okay, so first what we have to do, in order to check the phase, we need to refer to the saturated water table first and find out the value of T saturated. Okay, based on pressure P3 equal to 3 megapascal, so we can determine T saturated at state number 3, where T saturated equal to 233.90 degrees Celsius, and then compare with the value of T3 given, which is 350 degrees Celsius. Okay, so from the value, we found that T3 given is greater than T saturated at 3 megapascal, which means If the temperature given is greater than T saturated, so the phase will be superheated vapor. If the value of T3 lower than T saturated, the phase will be compressed liquid. But for now, because the T3 greater than T saturated, so the phase will be superheated vapor. And then you need to use the superheated vapor table to determine the enthalpy value for state number 3, and also the other value for state number 3. Okay, so now refer to superheated water table. Okay, find out the table for 3 megapascal, and the temperature rose at 350 degrees Celsius. So from this value, you can determine the value of H3, which is equal to 3115.3 kilojoule per kg, and also you can determine S3 equal to 6.7428 kilojoule per kg Kelvin. So you need to determine S3 because later on you need to manipulate the value of entropy in order to determine the data for state number 4. Okay, because the process is isentropic during the expansion process. Okay, for state number 4, the data given or the data available is originally we only have P4 equal to 75 kilopascal. But we know that during the process of expansion, the process is isentropic. So S4 automatically we will obtain the value of S4 from S3. S4 equal to S3 equal to 6.7428 kilojoule per kg dot Kelvin. Okay, so from this value we have already 2 data. So now we can determine the phase for state number 4. Okay, so in order to determine the for state number 4, we need to refer to the saturated water table. So now, previously for state number 3, we check the phase by referring to the pressure and also temperature. So now, because we only have the data pressure and also the entropy value, so we need to check in terms of phase by referring to the entropy value. Okay, what we have to do, at pressure of 75 kilopascal, we need to find the value of SF and also SG. SF represent the value of entropy at the saturated liquid condition, and SG is entropy value at the saturated vapor region as shown in the TS diagram. Okay, which is the limit for the upper limit and also the lower limit for the saturated mixture region. Okay, so the condition will be if the value of state number 4 greater than SG, the phase will be superheated. If the value lower than SG and in between the value of SF and also SG, okay, the phase will be saturated mixture. Okay, so if we look if we compare in terms of the value of SF, SG and also the value of S4, so S4 will be in between SF and SG, so the phase will be in saturated mixture. Okay, so now when the phase is saturated mixture, so we cannot determine the value of H or the value of H directly from the table. So as we have learned in thermodynamic 1, we need to determine the value of H by using specific equation, and also we need to determine the quality of the steam, value of X, before we can determine the value of H for state number 4. Okay, so for state number 4, in terms of enthalpy, so now we need to use we need to manipulate the entropy formula that we have learned in thermodynamic 1. So just rearrange the equation. From the equation, we can obtain the equation for the quality of steam at state number 4. X4 equal to S4 minus SF at 75 kilopascal divided by SFG at 75 kilopascal. Okay, so S4 we already obtained, SF and also SFG we can determine from the saturated water table at 75 kilopascal. Okay, and from the equation, if we substitute the value, so we can obtain the value of X equal to 0.8857, which is equal to 88.57%. the water consists of 88.57% vapor and the rest still in liquid form or liquid phase. And then use the formula for enthalpy that you have learned in thermodynamic 1, where H4 equal to HF at 75 kilopascal plus X4 multiplied by HFG at 75 kilopascal. So the value of HFG at 75 kilopascal you can determine from the saturated water table. Okay, substitute the value, so we'll get H4 equal to 2402.5 kilojoule per kg. And now we already obtained all the value for enthalpy, start from H1 until H4. So easily we can determine the value of Q in, where Q in equal to H3 minus H2 equal to 2727.88 kilojoule per kg. Q out equal to H4 minus H1 equal to 2018.11 kilojoule per kg. And then you can substitute the value of Q in, Q out into the thermal efficiency equation. So we will get the value of thermal efficiency for the ideal Rankine cycle for the example 4.1 equal to 0.260 or 26%.